Okay, so here's a quick problem just to show you how you can apply net torque to the moment of inertia times the angular acceleration idea. And we've got two torques, one being applied by a pedaling force out at a certain distance away on a bike wheel. Maybe that's the edge of the gear or the gear that you're in. And then a braking force is being applied slightly in the counterclockwise rotation out at the edge of the wheel. So the wheel in this problem, it says, can be treated as a thin hoop. And the moment of inertia of a thin hoop, if you look up in a table, is the mass of the hoop times the radius of the hoop squared. So we'll need that information later on. We can see the pedaling force is clockwise, so it's negative, and the braking force is counterclockwise, so it's positive. So our net torque equals I alpha. So just substituting in what we've got for the net torque, we can see that we've got our formula for torque applied to each of the forces at their positions, equaling I of the hoop times alpha. So again, from the table, looking up the moment of inertia of a hoop, it's the mass of the hoop times r squared. So I'm going to ignore the little disc of the gears for now. In the next problem, we'll take a look at how we might deal with something like that. But so from here on out, you've got the big idea, and now it's substituting in the values. So the 5 centimeters, convert that to meters, and we've got the 100 newtons, and both of the torques are being applied perpendicularly, so it'll be sine of 90, which will be 1. The radius of the bike wheel is 25 centimeters, 10 newtons, also sine of 90. The mass of the wheel is given as 300 grams, so I convert that to kilograms. The radius of the wheel was 25 centimeters, again convert that to meters. So we can solve for alpha. So we can see that the clockwise torque, negative 5 newton meters, plus the counterclockwise torque of the braking, 2.5 newton meters, divided by the moment of inertia quantity. Notice the units are kilogram meters squared because it's r squared m. And we come up with negative 133.3 radians per second squared for the angular acceleration, which is the clockwise direction. Okay? So the bike is going to accelerate forward, and since linear acceleration is equal to r alpha, we can take the radius of the bike wheel, 0.25 meters, and multiply by the angular acceleration. Notice we get a is negative 33.3 meters per second squared, but we know that the bike, if the wheel is moving clockwise, will be moving to the right. So I'm just going to say the magnitude of the linear acceleration is going to be 33.3 meters per second, and I know the bike's going to be going forward. All right, so that's just a quick problem on how you get started on using the net torque, the moment of inertia of a hoop, and calculating the angular acceleration, and then tying it back to the linear acceleration.